Here in this section, we have sequences. The first part definition, the sequence an converges to the number uppercase L if for every positive number epsilon there corresponds an integer n such that absolute value of an minus L less than epsilon whenever lowercase n greater than uppercase n. If no such number L exists, we say that an diverges. So here we have Z, and here on side we have an. If an converges to L, we write limit of an when n approaches positive infinite, that is equal to L, or simply an approaches L and call L the limit of sequence. Now here under definition, the sequence an diverges to infinity if for every number uppercase M there is an integer uppercase n such that for all n larger than uppercase n, an greater than uppercase n. If this condition holds, we write limit of an when n approaches positive infinite, that is equal to infinite, or in other words, here we have an approaches positive infinite. Similarly, if for every number m there is an integer uppercase n such that for all n greater than uppercase n, we have an less than m. Then we say an, the sequence, diverges to negative infinity and write limit of an when n approaches infinite, that is equal to negative infinite, or we can say an approaches negative infinite. Next part, here we have 3 in 1. Let an and bn, these two sequences, we have real numbers, and let a and b be real numbers. The following rules hold if limit of an when n approaches infinite, that is equal to a, and limit of bn when n approaches infinite, that is equal to b. The first rule is sum rule. Limit of an plus bn when n approaches infinite, that is equal to a plus b. Second rule, difference rule. Limit of an minus bn when n approaches infinite, that is equal to a minus b. So here on this part, we have difference and use subtraction. Number 3, constant multiple rule. So limit of k times bn when n approaches infinite, that is equal to k times b. The k is a number. Number 4, product rule. Limit of an times bn when n approaches infinite, that is equal to a times b. Number 5, quotient rule. Limit of an divided by bn when n approaches infinite, that is equal to a divided by b. And here b is in denominator, we cannot have that equal to 0. If you had 0 in denominator, you're going to have undefined. So for that reason, b is not equal to 0. Second term, here we have the sandwich term for sequences. Let an, bn, and cn be sequences of real numbers if an less than equal to bn less than equal to cn holds for all n beyond some index uppercase n, and if limit of an when n approaches infinite, that is equal to limit of cn when n approaches infinite, that is equal to uppercase L, then limit of bn, what we have here between these two, so limit of bn and approaches infinite, that is equal to same answer that we have here for cn and an, so that is equal to L. So for an and cn, when n approaches infinite, the answer here is L. We're going to have same thing for limit of bn, so here again we have L. So here again, theorem, the continuous function, theorem for sequences. Let an be a sequence of real numbers if an approaches L, and if function f continuous at L and defined as all an, then f of an approaches f of L. Theorem 4, suppose that f of x is a function defined for all x greater than or equal to n sub 0, and that an is the sequence of real numbers such that an is equal to f of n for n greater than or equal to n sub 0, then limit of an when n approaches infinite is equal to L, whenever limit of f of x when x approaches infinite, that is equal to L. To apply the following 6 sequences converge to the limit listed below. So the first one, limit of natural log n divided by n when n approaches infinite, that is equal to 0. Number 2, limit of nth root of n when n approaches infinite, that is equal to 1. Here on this part we have limit of x power 1 over n when n approaches infinite, that is equal to 1. So here in this case, using infinite here in denominator, we're going to have 1 over infinite and 1 over infinite, that is 0. So we're going to have x power 0. Having 0 as a power, it doesn't matter what we have here for base, that will be equal to 1. Then number 4, limit of x power n when n approaches infinite, that is equal to 0. And what we have here in this case, absolute value of x less than 1. Number 5, limit of 1 plus x over n power is n. When n approaches infinite, that is equal to e power is x. So, and for x, we have any number. Number 6, limit of on top numerator, we have x power is n divided by n factorial. When n approaches infinite, that is equal to 0. Here again, we have any x. So here in denominator, we have n factorial. Using infinite, we're going to have, it doesn't matter what we have on top. So any number divided by infinite, that will be equal to 0. In formulas 3 through 6, x remains fixed as n approaches infinite. Here again, we have definitions. A sequence an is bounded from above if there exists a number uppercase m such that an less than or equal to uppercase m for all n. The number m is an upper bound for sequence an if uppercase m is an upper bound for sequence an, but no number less than uppercase m is an upper bound for sequence an. Then m is least upper bound for this sequence. Here in this case, we have an. Next one, sequence an is bounded from below if there exists a number m such that, now here in this case, we have a sub n greater than or equal to m for all n. The number m is lower bound. So that is lower bound for sequence an. So the difference between these two, here on top we have an is less than or equal to m, but here an is greater than or equal to this lowercase m. So m is less than equal to a sub n, but an is greater than or equal to m. Based on what we have for m, that is less than or equal to. So that's why here say lower. But here on top, a sub n is less than or equal to uppercase m, and or we can say m is greater than or equal to a sub n. Because of having m greater than, here what we have for m, that is upper bound. And then here, if lowercase m is a lower bound for sequence an, but no number greater than m is a lower bound for sequence an, then this lowercase m is the greatest lower bound for sequence an. If sequence an is bounded from above and below, the sequence an is bounded. If sequence an is not bounded, then we say that sequence an is an unbounded sequence. Definition is sequence an is non-decreasing if an less than or equal to a sub n plus 1 for all n. That is a sub 1 less than equal to a sub 2 less than equal to a sub 3 less than equal to, we can use 3 dots here. The sequence is not increasing if a sub n greater than equal to a sub n plus 1 for all n. The sequence an is monotonic if it is either non-decreasing or non-increasing. Theorem 6, the monotonic sequence theorem. If a sequence an is both bounded and monotonic, then the sequence converges. Example, a formula is given below for the nth term a sub n of a sequence an. Find the values of a sub 1, a sub 2, a sub 3, and a sub 4. So what we have here for a sub n, that is equal to -1, power is n plus 1, denominator we have 10 times n minus pi. So the first part of finding a sub 1, what that means, n is equal to 1. So instead of n, we're going to use 1. So a1 is equal to -1 power, here for n we have 1, so we have 1 plus 1 divided by 10 times 1 minus 5. So this is equal to, on top we have -1 power 2. So that is positive 1. Denominator 10 minus 5, it is 5. So the answer for this one is 1 over 5. Now finding a sub 2. So instead of n, now we use 2. We have a sub 2 equal to -1 power 2 plus 1. Denominator 10 times 2 minus 5. So on top, numerator, we have -1 power is 3. We're going to have -1 on top, and denominator 10 times 2 is 20 minus 5 is 15. So here the answer for this part is -1 over 15. Now finding a sub 3, that is equal to -1 power, instead of n we have 3, so we have 3 plus 1 divided by 10 times 3 minus 5. So this is equal to, we have -1 power is 4, so that is positive 1. Denominator 10 times 3, that is 30, minus 5, we have 25. So the answer for this part is 1 over 25. And finally, finding a sub 4, so that is equal to -1, n is 4, so we have 4 plus 1, denominator 10 times 4 minus 5. So this is equal to, we have -1 power is 5, so this is -1. Denominator 10 times 4 is 40, minus 5, we have 35. So the answer for a sub 4 is -1 over 35. The first term of sequence along with a recursion formula for the remaining terms is given below. Write out the first 10 terms of the sequence. What is given here on this part, a sub 1 is equal to 7, and a sub n plus 1 is equal to a sub n plus 1 over 2, and here power is n. So we have 1 over 2 to the nth power. So here I want to find a sub 2. So what I used here for n is 1. So I used this one here. A sub 1 equal to 7. In this case, n is 1. So to have a sub 2 using this part, instead of n, we have to use 1. So we have a sub 1 plus 1, that is equal to a sub 1 plus 1 over 2, and here power is 1. Based on what is given on top, a sub 1 is equal to 7 plus 1 over 2. So here on this part we have 2 times 7, we have 14 plus 1. So the answer is 15 over 2. Now on this part, finding a sub 3. So in this case, what we have for n, that is 2. So a sub 2 plus 1 is equal to a sub 3. And here a sub 3 is equal to, instead of n, use 2. So we have a sub 2 plus 1 over 2, and here power is 2. A sub 2 is equal to 15 over 2 plus, here we have 1 over 4. Now simplify. The denominator 4, here we have 2 times 15, that is 30, plus 1. So we have 3, 1 over 4. That is the final answer for a sub 3. Now finding a sub 4, we have n equal to 3. So we have a sub 3 plus 1, that is equal to a sub 4. So here we're trying to find a sub 4. That is equal to, instead of n, now here we have 3. So that is a sub 3 plus 1 over 2, power is 3. And a sub 3 from here, this part is 3, 1 over 4 plus 1 over 2 cubed, that is 1 over 8. So denominator we have 8, and we're gonna have 62 plus 1 here on top in numerator. So what I did, I multiplied this by 2. So 2 times 4 to have same denominator. That means that we have to multiply same number here on top. So 2 times 31, that is 62 plus 1. Our final answer is 63 divided by 8. Now this part n is equal to 4. And here we want to find a sub 5. So what we have here, instead of n, use 4. So a sub 4 plus 1, that is equal to a sub 5. And a sub 5 is equal to a sub 4 plus 1 over 2 to the 4th power. And a sub 4 from this part is 63 over 8 plus 1 over 16, and that is equal to, here denominator 16, and here multiply by 2, both numerator, denominator, and then add 1. So a sub 5 is equal to 127 divided by 16. Now here finding a sub 6, that is equal to a sub 5 plus 1 over 2, power is 5. That is equal to a sub 5 is 127 divided by 16 plus 1 over 2 to the 5th power, that is equal to 32. Now simplify. So this is equal to, denominator we have 32, and on top 2 times 127, and then add 1. So a sub 6 is equal to 255 divided by 32. Now here on this part we have a sub 7, that is equal to a sub 6 plus 1 over 2, power is 6. This is equal to a sub 6 is 255 over 32 plus 1 over 2 to the 6th power, that is equal to 64. Now simplify. So here denominator we have 64. Multiply this 1 by 2. We have 2 times 255. Then add 1. So the final answer is 511 divided by 64. Now finding a sub 8, that is equal to a sub 7 plus 1 over 2, power is 7. This is equal to what we have for a sub 7, that is 511 divided by 64. 1 over 2 to the 7th power is equal to 128. So that is here in denominator. Now simplify. So this is equal to, in denominator we have 128. Multiply this one by 2. So we have 2 times 511. Then add 1. So the final answer is 1023 divided by 128. And now here on this part we have a sub 9, that is equal to a sub 8 plus 1 over 2 to the 8th power. This is equal to a sub 8 from this part is equal to 1023 divided by 128 plus 1 over 2 to the 8th power is equal to 256. Now simplify. So here in denominator we have 256. On top we have to multiply 1023 by 2. So we have 2046 and then add 1. So final answer is 2047 divided by 256 for a sub 9. And finally here finding a sub 10, that is equal to a sub 9 plus 1 over 2 to the 9th power. That is equal to, for a sub 9 we have 2047 divided by 256 plus 2 to the 9th power, that is equal to 512. So here on this part we have 1 over 512, and then simplify. Here denominator we have 512. So multiply this by 2, we have 2047 times 2, that is equal to 4094, and then add 1. So final answer here for a sub 10 is equal to 4095 divided by 512. Example, find a formula for the nth term of sequence. What is given here on this part, we have 1, negative 32, 243, negative 1024, positive 3125, 3 dots. So here we have 3 dots. What that means, we have infinite sequence. So infinite sequence of numbers is a function whose domain is the set of positive integers. So here what we have on this part, the first one is A1, the second one is A2, we have A3, A4, A5. So finding a formula for the n term of a sequence, whose terms are a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, 3 dots, is equivalent to finding the function a sub n for the sequence with n greater than equal to 1. So to determine the function, we have to see what is the relationship between these numbers for A1, A2, A3, and A4, and A5. So the first number here we have is positive 1, the second number is negative 32, and the third one is positive again, and the A4 is negative, A5 is positive number. So what we have here for A1, that is 1. For A2, we have negative 32. So let's just first use that one, 32. That is 2 to the 5th power equal to 32. And then A sub 3, that is 243. And that is 3 to the 5th power. What we have here is negative 1024. So without using this negative sign, what we have is 1024. So that is 4 to the 5th power. And here 3125 is 5 to the 5th power. But the point is that here we have negative and here we have negative sign. So each term alternate sign, we have positive and then we have negative, again positive, negative, and again positive. So what I used here on this part, in the first part, I used absolute value. So I used this one, absolute value of A1, that is equal to 1 to the 5th power, absolute value of A2, that is 2 to the 5th power, absolute value of A3, 3 to the 5th power, absolute value of A4, that's 4 to the 5th power, absolute value of A5, that is 5 to the 5th power. So what I use is absolute value of A sub n equal to n to the 5th power. But the point is that here on this part for A sub 2, we should have negative, here positive, here negative, here positive. So the first one is positive. I use negative 1 power n plus 1, and the first one, n, is equal to 1. So we have 1 plus 1 power is 2. Negative 1 to the 2nd power is positive. So that way I got positive sign. And then for second sequence, for A sub 2, here we have negative 1 power 2 plus 1, so instead of n we have 2. 2 plus 1 power is 3. So we have negative 1 to the 3rd power, and that's how we got negative sign. For A sub 3, we have n is 3, 3 plus 1, that is power, so negative 1 to the 4th power, here we have positive. For A sub 4, we have 4 plus 1, power is 5, so negative 1 to the 5th power, we have negative sign. Here for A sub 5, n is 5, so 5 plus 1, power is 6, negative 1 to the 6th power is positive. So we have positive, negative, positive, negative, positive. And then multiply by what we had from this part. So the first one is 1 to the 5th power, second is 2 to the 5th power, here we have 3 to the 5th power, 4 to the 5th power, and 5 to the 5th power, and we have exactly same numbers that were given here on top. So based on these two steps, our formula is a sub n equal to -1 power n plus 1 times n to the 5th power, where n is greater than or equal to 1. So that the recursively defined sequence converges and find its limit. So what is given? A sub 1 is equal to -19, and a sub n plus 1 is equal to square root of 77 plus 4 times a sub n. Since it is assumed that the recursively defined sequence converges, the limit exists. Let x be the value of this limit. So a sub n approaches x. After the limit has been reached, the value of these two terms, a sub n and a sub n plus 1, will be indistinguishable from x. So using this assumption, what we have here for a sub n plus 1, so based on what is given on top, we have square root of 77 plus 4 times a sub n. We're going to have, so using x for a sub n plus 1, that is equal to square root of 77 plus 4 times x. So we have same thing for a sub n plus 1 and a sub n. So instead of these two, I used x. So what we did on this part, the formula for a sub n plus 1 will approach the formula for x as n approaches infinite. And then next step, we have to solve for x. So here we have square root. So we have to eliminate that, and by using second power on both sides, so we have x squared equal to 77 plus 4 times x. So here we have x squared minus 4x minus 77 is equal to 0. And then factor, here we have x minus 11 times x plus 7, that is equal to 0. So solving for x minus 11 equal to 0, x is 11, x plus 7 equal to 0, x is -7. So x is either -7 or positive 11, but limit cannot have two different values. Since the value of a sub n plus 1 will always be greater than or equal to 0, so the answer should be greater than or equal to 0 in this case. But we have x is positive 11, so the limit cannot be negative, meaning that the sequence converges to positive 11. So this is our final answer for this part. Example, does the sequence a sub n converge or diverge? Find the limit if the sequence is convergent. What is given, a sub n is equal to 4 minus 8 times n to the 4th power divided by n to the 4th power plus 9 times n cubed. So to find the given limit, first divide the numerator-denominator of the expression by the largest power of n that we can find in either numerator or denominator. So in this case, the largest power is n to the 4th power, so divide both numerator and denominator of a sub n by n to the 4th power. So a sub n is equal to divided both numerator and denominator by n to the 4th power, and then we have to simplify. So we have 4 over n to the 4th power minus 8 times n to the 4th power divided by n to the 4th power, and here in denominator we have n to the 4th power divided by n to the 4th plus 9 times n cubed divided by n to the 4th power. Simplify, we're going to have 4 divided by n to the 4th power minus, this part cancels, so here we have 8 divided by n to the 4th divided by n to the 4th, that is equal to 1 plus, here simplify, so we're going to have 9 over n. Now finding limit when n approaches infinite. So this is what was given. We have 4 minus 8 times n to the 4 divided by n to the 4 plus 9 times n cubed. So what we did here on this part, a sub n is equal to this part. So use this one here to find limit. But this is equal to limit of 4 over n to the 4th minus 8 divided by 1 plus 9 over n. This is when n approaches infinite. Now evaluate limit. So here we have 4 over n to the 4th power. So we have that one here. Instead of n, now we use infinite. So in denominator we have infinite. On top we have a number. So 4 over infinite, that is equal to 0. And same here for this part, limit as n approaches infinite. Here we have 9 over n. Instead of n, we have infinite. So this is equal to 9 over infinite. Because of having infinite in the denominator, our limit is equal to 0. So to find the final answer for this part, this is equal to, we had 0 based on what we had here on this part, and then subtract 8. So you have that part here. In denominator we have 1 plus 0. So the answer is negative 8 over 1. So that is negative 8. Since limit of a sub n as n approaches infinite is equal to negative 8, the sequence converges. So here we have limit and sequence converges.